paper is co-authored by J.C. Chang, and is given by Professor Burwell of Northeastern University in Evanston, Illinois. His award of Kendall Award was in 1973, and at that time she spoke about modified silica gels as adsorbents and catalysts. Today he will speak about carbonaceous deposits on metal. First of all,
thank you, and thank you for the invitation to speak. But I was wondering if you decided to withdraw the invitation. I will, well, I didn't know whether it was a hint or not. Shall I talk?
You can overcome it, Tom.
Shall I talk anyway?
Yeah.
Well, you said so now. So, if you run a hydrocarbon reaction on a metallic catalyst in the absence of oxygen, in addition to your desired reaction, you almost always get the deposition of some kind of a hydrocarbon or carbonaceous residue. And I'm going to talk this morning just about the case for a few particular metal catalysts, platinum, palladium, and nickel on the one hand, and molybdenum on the other hand, and at low temperatures, not about the case at high temperatures. Now we can start with the work of Otto Baek back in the 40s. And Baek considered that, from his data, that you start off with a clean surface. Now we introduce the hydrocarbon and hydrogen. It's immediately covered with whatever reacting species are leading to your final product, but then slowly you form slowly reacting species of hydrocarbon, or adsorbed hydrocarbon. And they had a formula for about CH, and Baek called them acetylenic residues, and he would write it like this, although he didn't really, I think, mean precisely that he had acetylene there. And so it slowly forms, it slowly reacts, and it comes to some steady state. And from Baek's calculation, the fraction of surface that was clean was very small. Nickel was only about a hundredth to a tenth of a percent. It was actually clean, and that was where all the reaction took place. The rest of the surface was poisoned, and even the catalyst, the metal, these are for evaporated metal films, even the metal that had the fastest reaction, rhodium, only 1% to 10% was clean according to Baek's calculation. Well, this work attracted some attention and controversy. Jenkins and Radil did some work in which they supported Baek's basic idea of the formation of the residues and their slow reaction. And it has been started very early in Eichen's early work. It's been continued up to the present by people like Norman Shepard. Have looked at it rather carefully. Now, in the early work of Eichen's, he looked at nickel silica, and he could see that if he put on ethylene, in this case at 150 or at lower temperatures, you got adsorption, but very weak CH bands. Whereas if now you exposed it to hydrogen at low temperatures, the CH bands increased a great deal, but if you pumped off the hydrogen, they went down, you could go back and forth. So clearly, in this case, there are two kinds of species. There are species which are reacting relatively fast, in this case to give ethane, and there are species which are formed which react and come off very slowly. And now, what about it? Well, I got interested in this personally by the following experiment a few years ago. Seems just like yesterday. we were passing 3-methylhexane and hydrogen over a nickel silica catalyst, about 120. And the compound was racemized, but not hydrogenalized or isomerized skeletally at this temperature. And the rate would look something like this. As you increase the pressure of hydrogen, the rate goes steadily down. Now you can come back, you retrace the curve. But suppose we take the case where we start off with 90 torr of hydrogen, and we get this by using a flow of hydrogen and a flow of helium, giving us the desired composition. So here's this point. Now we turn off the hydrogen. Just have pure helium now. The rate jumps up, should, but then it steadily falls like this with time. And each one of these points might be maybe 20 minutes apart. You have to collect enough 3-methylhexane to put on a polarimeter tube. So it falls. And now put back the hydrogen. Now the rate slowly starts to climb. So here was a very clear example of the formation and removal of these carbonaceous residues. And I thought that this was a very nice experiment. You could elaborate it by putting deuterium here instead of hydrogen. Now you've got isotopic exchange as well as racemization. Most of the exchange was multiple. The ratio of exchange to racemization was now independent of the pressure. So here we could measure the rate of isotopic exchange when we don't have any deuterium present. And this seemed nice. I must say that apparently nobody else thought this was nice. I still think it's nice because as far as I know, there's never been a reference to this experiment in the literature. So I take one last try at it. We came back to this some years later in the following experiment. We were running isotopic exchange of cyclopentane and deuterium, about 80 degrees, in a platinum silica catalyst. Now we're passing a mixture of cyclopentane and deuterium over the catalyst. The silica gel over here is warm, so everything passes through the silica gel. We sample it with a gas chromatograph and get the rate of exchange and the phenomena and so on. But now, after running the reaction for a while, we flush it for some minutes with with helium to get rid of all the hydrocarbon. And then we start a flow of hydrogen and cool the trap to liquid nitrogen. It will not connect any hydrocarbon. And so we run it while we warm the catalyst. We keep the flow of hydrogen. And when we get to 100 degrees, we abruptly warm the trap, analyze the product. It's entirely cyclopentane, nothing else. Now we go to 200 degrees. We don't collect anything now. 300 and then 450, a little methane. So overall, it might be nice. Could somebody push that thing just slightly? Or is it tied to the floor? That's going to say cyclopentane when we get it.
Put it on the floor. Wait.
Macro effect.
Very good. The ratio of cyclopentane to surface platinum atoms was a 10, and of methane to platinum surface atoms, quarter of 5, so there was 10 times as much carbon in the cyclopentane as in the methane. So again, we see the formation of some slowly reactive hydrocarbon residue, but there are two kinds. Whatever kind leads to high temperature methane, and some that has an unchanged carbon skeleton of cyclopentane. Pentane gave exactly the same result, and so did 2,2-dimethylhexane in exchange with deuterium. This is true both on platinum silica and palladium silica. No isomerization. Now at a lower temperature, ethylene and cyclopropane gave, upon warming, only the hydrocarbon, unchanged structure. Of course, this is bound to be open. And then no methane at higher temperature. So again, we see there must be at least two different kinds of hydrocarbon residues. Probably there are 27. Now, surface chemical physics gives us some ideas here that are useful. If I take ethylene and adsorb it on 111 platinum, I get this ethylidine species, which will pick up a hydrogen atom, but then further removal by hydrogen is quite slow. Now, of course, with cyclopentane, I can't very well make an ethylidine species, but I can make a cyclopentadienyl species, which also is rather stable. So, at least in part, those surface species that I'm talking about might look something like this. Well, now, so much for the group 8 metals. Let us say a few words on molybdenum. We happen to be making these supported molybdenum, metallic molybdenum catalysts in two ways. Either you can decompose molybdenum hexacarbonyl on highly dehydroxylated alumina, Da, and you get off most of the carbon monoxide, but there's some carbon and oxygen left, and if you heat that in hydrogen to 950, it's removed, and you have metallic molybdenum on alumina, dehydroxylated alumina. Now, we can start with molybdenum hydride on hydroxylated alumina, heat it in hydrogen to 950. There's very little loss of, some but very little loss of surface area. And we get the same species, and furthermore, they got about the same particle size, and physically and chemically, we can't tell them apart. They have interesting catalytic properties. For the hydrogenolysis of propane, they give two reactions. They form methane and ethane as one reaction, but an independent reaction, an initial product, forms double hydrogenolysis to 3 methanes, about 250 degrees. Cyclopropane, again, two reactions, simple ring opening and a sort of double hydrogenolysis. This is, there's only one catalyst known that's clearly more active than this, that's ruthenium on alumina for a supporting catalyst. Hydrogenation of olefins, it's as active as platinum. And in the exchange of deuterium with deuterium of alkanes, it's about as active, probably more active than any other catalyst that's been reported. So it's interesting, but now the question is, molybdenum is probably having a very large heat of sublimation. This probably should be expected to be a very aggressive metal in reacting hydrocarbons. So is the catalyst a metallic molybdenum, or is it a molybdenum carbide which would be formed in the first minute or half minute of reaction? Now, Boudard has looked at these rather a lot, and there's no doubt that the carbides are catalysts. But what are they here? And in particular, what are they at the first instance? Can molybdenum metal be a catalyst, or is it always converted to a carbide? Well, let's look at the hydrogenolysis of propane, 250 degrees flow reactor. There's some deactivation, about 15% in the first hour, but then very little in the remaining 9 hours. Well, you could say here, of course, it's carbide, because in the first minute where you can't make any measurements, it's all converted to carbide, and then after that carbide's a reactant. Oh, all right, let's try pulses of propane injected into a flow of hydrogen. Now each one of these has a contact time of about 6 seconds only. And what we find is that there's essentially constant conversion for pulse in this particular experiment at 25% conversion. And after pulse 5, we measure the amount of carbonaceous residue by heating to 950 degrees in hydrogen and measuring what comes off. And it's only methane appears. And we have 0.04 methane per molybdenum surface. So in one pulse, after one pulse, we can't measure the loss in hydrocarbon. It's too small for the technique, but it's probably in the vicinity of 0.01. And it seems very unlikely now, in this case, that we're forming hydrocarbon, a carbide layer at the beginning of that pulse, and then getting all the other carbide formed later being ineffective. So that here I think we can be reasonably sure that at least at the beginning, metallic molybdenum is a genuine catalyst. And the methane comes off about half between 300 and 500 and half above it. Now, if we try another reaction, hydrogenolysis of methyl cyclopropane, pulse reactor, 100 degrees, constant conversion per pulse. After pulse 5, the turnover number is 10. That is, 10 molecules of methyl cyclopropane have reacted per surface atom. Notice I say turnover number here, which is the proper term here. Turnover frequency is a rate. And then the molybdenum surface methane inverse ratio is here. And now 2/3 of the methane is liberated at a low temperature. I think we can make two conclusions: that metallic molybdenum is certainly catalytically active. I don't say anything about what happens late in the reaction, but initially it's active, and but this begins to be a bit high, and maybe there's some of the deposit may be actually on the surface of the alumina. Now, the last reaction I will mention is hydrogen and propylene at minus 45 degrees in the flow reactor. And this is as I already mentioned, it's quite an active catalyst. We can't use a pulse reactor here because propylene is absorbed quite strongly on alumina at the temperature I have to use to measure the reaction. So we have to ignore any propylene that comes off as probably being from the alumina. So we only measure the methane. And now, as far as the total conversion goes, there's about a 50% decline between 0 minutes and 60 minutes, following which the decline is quite small. Well, after 4 minutes, the methane of molybdenum is about 0.2, so that it looks very unlikely that we've converted the surface to carbide in a minute at minus 45 degrees. 100 minutes, it's gotten quite large. So here it seems almost sure that some of the deposit is in fact on the support. Well, this would be no surprise to those who worry about such things. That must be true in many cases, particularly in hydrocarbon reactions industrially at high temperatures. So then, there's, again, surface chemical physics provides some useful information here. Overbury shows that ethylene absorbs with extensive dissociation on molybdenum 111, 25 degrees. The dissociation produces a non-carbidic form of carbon, which dives just below the surface at about 325, although it stays within a nanometer or so of the surface. Still higher temperatures, it goes into the bulk. And my colleague right upstairs from me has found that, studied the reaction of cyclopropane with hydrogen on 110, and he finds both single and double hydrogenolysis, just as we had found earlier, and he found that it goes considerably faster on clean than on carbon-covered surfaces. So then I think we may make the following conclusions: that clean metal is catalytically active, but that substantial amounts of slowly reacting residues gradually develop. These, we think, are poisonous, in following Bake's original idea in this case. Now, in the case of nickel, platinum, and palladium, these deposits are removable if you just warm 50 to 100 degrees above the temperature of the run, for the most part. But as you begin to go to higher temperatures, you begin to find deposits that come off only at much higher temperatures as methane. And the residue is non-uniform. There's more than one species. Now on molybdenum, clean molybdenum is catalytically active. 5 minutes? How about 1 minute? Hydrogen liberates 95% of the residue as methane, but perhaps by hydrogenolysis of some initial residue that has more carbon in it. Residue again, there's more than one kind, which is hardly a surprise. And some residue may be on the support, and we cannot say really at long times whether some of that carbided surface is being a catalyst or not. It may be true. Thank you.
Thank you, Professor. Well, my apologies for any clerical errors that might have come anywhere.
Well,
I apologize for my errors that might have come.
No, I didn't learn about it until I arrived here this morning. Of course, if I'd seen it earlier, I might not have come. I felt like the come, but
I distributed until and looked at until right now. The paper is now open for discussion. We have a few minutes. Yes.
I wondered in the hydrocarbon fragment buildup, the residue, whether you had any evidence for the propensity to actually make carbon bonds form graphitic type overlayers, or whether you thought it was all going to.
I don't think we get graphitic overlayers at this temperature. Do you?
I would say on some of the more noble metals that around your upper limit, we have some SIMS evidence for, in negative ion SIMS, for the growth of inverse of C2s. That's starting from that point.
In the presence of hydrogen.
In the presence of small amounts of hydrogen. You can't hydrogenate that material off very readily. I don't know about the molybdenum or the ruthenium, which I would suppose made carbides first.
On the platinum and palladium, for reactions run at 0 degrees or below, all of the residue comes off with the original structure by just a little bit above it. On the other hand, at those exchange reactions which were running around 100 degrees, about 10% of it came off only when you went to rather high temperatures, and now it's methane. And so I guess you could conceivably say that that was due to some graphite-like material. It's not a large fraction total at the times on stream we use, which were not large. They were over 20, 30 minutes.
My recollection is for ethylene, you found that around 600 Kelvin, you started to grow these inverse. You never broke the carbon-carbon bond. You started making carbon-carbon bonds, which still had a lot of hydrogen in it, but nevertheless were losing hydrogen slowly. So that's
but our reactions were below 300 Kelvin with ethylene.
Below 300 Kelvin. Okay,
we had to run them at, those reactions, the one I mentioned, were run at minus 31 centigrade. The hydrogenation of ethylene and the hydrogenolysis of cyclopropane at 0. We couldn't run it any higher because of the rate of the reaction. But the alkane reactions, those alkane exchange, they run near 100. Sorry, centigrade.
Bob, have you been able to attribute the double hydrolysis to form two methanes, to any particular species, let's say the Philippine species?
Well, I've tended to think the simplest thing to do was to take the Rooney mechanism, which involves something that looks like a metallocyclopropane, and which we know in olefin metathesis cleaves to something like an adsorbed ethyl and a methylene, which give you ethane and methane. And while I don't know any strong evidence for that, it's consistent with the data, and it's the simplest form I've seen. I prefer it to anything else.
Even on molybdenum 0?
Even on molybdenum 0.
Bring the hips in for us. Thank you very much.
Thank you.